what we are going to learn today is derivative graphs or graphs of derivative. Okay, pretty interesting a topic. Pretty interesting a topic. Now, before we understand the derivative graphs, let's understand the key concept of derivative. As in we did that last week. But what exactly is derivative doing to my function? So if I have a function f of x equals to x raised to the power of n, and I say f dash x, so what is that? N x raised to the power of n minus 1, right or wrong? That is what we know. So what exactly is it actually doing to us? It is reducing the power by 1, right? It reduces the power by 1. So if you have a, y equals to x cube, derivative makes it 3x squared. So a cubic becomes a quadratic, right? That's what's happening. So you just need to take care of that, and you need to understand that. So when you're given a graph and you're asked to find the derivative of that graph, you're asked to find the derivative, you have to graph the derivative of that function. So whenever you're given a function's graph and you're asked to graph the derivative of that, always remember that you need to go 1 degree down. So if you're given cubic, you should be getting a quadratic when you graph it by hand. So if you're not getting it, that means there's something wrong. If you have a quadratic, it should become linear. So if I have x square, what does derivative makes it? A linear, 2x. If you have a linear 2x, it makes it a constant graph which is parallel to the x-axis. And if you have a constant graph, derivative is 0. The slope is 0. Slope of the horizontal line is always 0, right? So slope of a constant is why 0. So just understand that flow, that you just need to go 1 degree down. That's about it. That's number 1. Let's try to pick one up. Let's try to draw a derivative graph, and the easiest one to draw or probably explain is a cubic to quadratic. Easiest one. That covers pretty much all the concepts. So let's say I have this kind of a graph of cubic, right? This is x, this is f of x. And I know the turning point. Let's say this is -1 and this is 1. I now need to draw the derivative graph of this cubic. So the first step that I will do is I will exactly replicate the axis underneath it. And I will say this is x and this is the f dash x now, because I'm drawing the derivative graph. So y has to be derivative, f dash x. F dash x is what? Nothing but the slope, m. Correct? So y-axis now represents the derivative, and because I'm drawing derivative graph. Whatever are my turning points of my graph, they become the x-intercepts of the derivative graph, -1 and positive. They become the x-intercept. That's the Next step, I'll probably make some space. Now, you tell me, from this point onwards, I'm coming from what? Negative infinity to -1. What is the nature of the slope? When I say nature, slope can be positive, negative, or zero of the tangent, because derivative is the slope of the tangent drawn at a point. What is the nature of the slope of the tangent? From negative infinity to 1, what's the nature? So when I say nature, if I draw a tangent here, I draw a tangent here, I draw a tangent here, and I draw a tangent here. All of them are a positive slope. Yes or no? They're all positive slope. Anything which goes like this is a positive slope. Anything that goes like this is a negative slope. Anything that is a straight line is a zero slope. Correct? So from negative infinity to -1, not at -1, just before -1, the slope is positive. The slope is very sharply positive when I am coming from negative infinity, and it slowly starts to become less positive, and eventually at x equals to 1, the tangent becomes parallel to the x-axis and slope becomes 0. Yes or no? Correct? Is this the right statement? Now let's draw this pattern here in the derivative graph. My y-axis is now the slope. And what is happening to the slope? The slope from negative infinity to -1 is very positive, highly positive, and eventually it is becoming 0. When I'm here, the f dash x, the y-axis, is 0. Am I making sense? Right? So, this portion of the graph, the green portion of the graph, is represented by the green portion of the derivative graph. Now let's change now, and at -1, I've hit the x-axis of the derivative graph, which means the slope or the f dash x is 0. Now what happens the moment I cross -1 until this point, which is 1? Let me draw the tangents. Tangents become negative, 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 extremely negative, eventually less negative, and 0. Let's replicate this here. From 0, the slope becomes negative, which means I have to slide under x-axis of the derivative graph. Why? Because this zone is slope negative, this zone is slope positive. And I've been sharply negative to eventually less negative, and I hit back 0 at x equals to 1. So I'm sharply negative, and then I sort of bounce back, I become less negative, and eventually I hit a 0 back. And you see now, the quadratic is taking some shape here. I am at this point now when my slope is 0 again, which means I'm here. And what happens here? The tangent starts to become positive. which means I go back into the positive zone of the derivative graph's y value, which is this zone. And this goes up till infinity. This goes. So finally, of the cubic, I am eventually getting a quadratic. That, in a nutshell, is how derivative graphs work. So to summarize, you just make the x-intercepts of the derivative graph equal to the turning points of the original graph. And you simply then, between the turning points of the original graph, you just keep tracking the positivity or negativity of the slope. And you just draw it here.